Okay, so in this lesson, we're going to talk about Fourier sine and Fourier cosine series. So before we start on that directly, we need to talk about even and odd function. Okay, this is an important subtopic that we need to know separately before we dive into the real point of this topic. So what are even and odd functions? Okay, first, let us discuss an even function. An even function is a function such that, okay, suppose I have f of x, and I tell you that this function is even. Okay, an even function is a function such that it satisfies the relationship f of negative x is equal to f of x. Okay, in other words, if you are presented with a function with, let's say, f is negative 100, then effectively what you can say that this result is the same as f is equal to 100. Okay, in other words, you simply remove the negative sign if it's an even function, okay? Provided that f is an even function. So this is what it means to be an even function. Now, this property will give rise to some interesting graphical properties. Okay, what do I mean? Meaning, if you plot an even function on a graph, right, there is one special property that it has. Okay, so let's read here. Graphically, it is symmetrical about the y-axis. Okay, all even functions satisfy this property that they are symmetrical about the y-axis. So this, right, will be a mirror. Okay, so this side will be symmetrical to this side. Okay, and this is true for all even functions. So next we have the odd function. Okay, odd function is if I tell you f of x is an odd function, okay, it is a function such that if you give f is equal to negative x, then the result is negative f of x. Okay, so the difference is that instead of removing the negative sign from the inside, this negative sign will effectively hop outside of the function. Okay, yeah, so hop outside of the function. So this is what it means to be an odd function. Okay, now this property also gives rise to its own graphical property, namely, it is rotationally symmetrical about the origin. Okay, rotationally symmetrical about the origin. So what I mean is that you treat the origin as a fixed point. Okay, a fixed point, like a clock. Those old analog clocks. Okay, these are the hands of the clock, right? So what I mean by a fixed point is I'm talking about this. Okay, where the hands turn around. So same thing, you treat this origin as a point where the graph turns around, and you can see that if you rotate this side of the graph 180 degrees, it will exactly line up with the left hand side of the graph. Okay? So that's what it means to be rotationally symmetrical. Okay, so all odd functions satisfy this graphical property that they are rotationally symmetrical about the origin. Okay, so let me give you a helpful tip of how to remember the even and odd function and its name and its property. Okay, when I say property, I mean the fact that for even functions, f of negative x is equal to f of x, and for odd functions, f of negative x is equal to negative f of x. Okay, so how do you remember this? So we need to look at the examples, the very basic examples of odd and even functions. So let's start with even function. We know that by definition, even function is a function such that f of negative x is equal to f of x. Okay, so you can throw away the negative sign inside. Now, what are the most basic examples of even functions? Okay, I'm going to show you a list of basic examples of even functions. Okay, x squared, x to the 4, x to the 6, x to the 8, and so on. Okay, you notice that all of them have even powers. Okay, keep in mind, even powers. Okay, so these are polynomials. Okay, polynomials. Yeah. Polynomials are functions in the form of x to the n. Okay, x to the n. This is the most basic form of polynomial. Okay, so yeah, n is an integer, meaning it can be either 1, 2, 3, 4, 5, 6, and so on. Okay, just integers. So when you consider even powered polynomials like this, they are in fact even functions. Okay, you don't believe me? Let's take a look at this. Okay, f of x is equal to x squared. Okay, so now let us test if it is an even function. So substitute negative x inside, what will you get? You will get, okay, negative squared is just positive. So in the end, your result will be x squared, right? So you see, notice that x squared is actually f of x, right? You see, x squared is equal to f of x. Therefore, this is equal to f of x. And so f of negative x is equal to f of x. See, this satisfies the even function property. And you can do this with x to the 4 as well, right? F to the x is defined to be x4, okay, x to the 4. Now let us test if it's an even function, okay? So you substitute x with negative x, and then negative 1 to the power of 4 is still positive 1, okay? Still positive 1. So in the end, your result will be this. And then you know that x to the 4 is equal to f of x. See, it still satisfies the uh, even function property. Okay, the even function property. And you can do this with all even powered polynomials. Okay, so that's an easy way to remember why is it called an even function. Okay, it's because for polynomials, okay, for even powered polynomials, they will satisfy this property. Okay, so that's how you remember that it is called even function. Okay, but you need not be polynomials. Okay, you need not be polynomials. And in fact, the most important example, right? The most important example that we are going to look at is cosine. Okay, cosine is considered to be an even function. Okay, cosine is considered to be an even function. This is the example that you should remember. Okay, this is important because we'll see this a lot in Fourier cosine. Yeah. Next, let's move on to odd functions. So odd functions, instead of even powered polynomials, now let's look at odd powered polynomials. So x, x to the 3, x to the 5, and so on. Okay, and you can test this. So let's say we have f of x defined to be x. So if I have f of negative x, this will be negative x, right? And then we can replace x with f of x, right? So if you do that, your left-hand side will become negative f of x. See, it satisfies the uh, odd function property. Okay, it satisfies the odd function property. Okay, you can do this with all other odd polynomials and find that they're the same thing. Okay. So what's the most important example of an odd function that you need to know for this? The most important example that you should know is sine. Okay, sine is an odd function. Okay, sine is an odd function. Now let's take a look at the graphs of cosine and sine and see whether they match the graphical property that I introduced to you just now. Okay, meaning is cosine really symmetrical about the y-axis, and is sine really rotationally symmetrical about the origin? So let's take a look. Yeah. So let's take a look at cosine. Okay, as you know, cosine for 0 to 2 pi should look like this. Okay, so if I extend this to the left, right, into the negative x region, it will look like this. You see? When I repeat this for 0 to negative 2 pi, notice that this graph, okay, the graph f of x equals to cosine x, it is symmetrical about the y-axis, right? The y-axis, you can treat it as a mirror line, and then the right-hand side is reflected onto the left-hand side. So it does satisfy the graphical property of even function. Namely, it is symmetrical about the y-axis. Now let's take a look at sine. Okay, so for sine, it will look like this. This is for one period, so 0 to 2 pi. This is f of x is equal to sine of x. Okay. Okay, so if I extend this into the negative x region, it will look like this. You see? Agree with me that this graph is rotationally symmetrical. It is rotationally symmetrical about the origin, right? It is rotationally symmetrical about the origin. So indeed, it does satisfy the graphical property of odd functions. Okay, so long story short is you need to know the two examples of an even and odd function. Okay, so even function, the most important example is cosine for our discussion of Fourier cosine, Fourier cosines. Yeah, yeah. So cosine x is an even function, which means that cosine of negative x will be cos of x. Whereas for odd functions, our most important example is sine of x, where if you take sine of negative x, it will give you negative sine of x. Okay, and then you also need to know how to draw these respectively. Okay, most important takeaway for graph sketching is even functions are symmetrical about the y-axis, odd functions are rotationally symmetrical about the origin. Okay, you need to know this because we're expected to sketch some graphs. Okay, so having said this, okay, so these are important formulas that you need to remember. So the definition of Fourier cosine series of a function, okay, so you are given a function, okay, a periodic function, okay, you're given a function. So if I want the Fourier cosine of f of x, okay, to obtain the Fourier cosine of f of x, we go back to the Fourier series that we talked about last week, okay? Fourier series, okay, remember, for Fourier series, it is f of x is equal to a naught plus okay, so this is a Fourier series in general. But now we restrict to a special case of the Fourier series, namely Fourier cosine and Fourier sine. So Fourier cosine is a if I want the Fourier cosine of f of x, what I need to do is okay, b bn will be treated as zero. Okay, so this entire term will drop, and then cosine, okay, the a naught term will still exist, and the cosine term will still exist. Okay, and as before, a naught and an are given by the formulas that we discussed last week. So I'm not going to go through that. Okay, so the graph of this is an even function. Namely, you should expect, right, that this should be symmetrical about the uh, y-axis. Yeah, symmetrical about the y-axis. So let's just say, for example, half of it looks like this, right? Then you should expect that the other half will be something like that. Okay, something like that. Okay, just as an example. Now, let's say I want the Fourier sine series of a function instead. So Fourier sine series is a function such that a naught is zero, okay, an is zero, and the sine term will continue to exist. Okay, the sine term will continue to exist. Now, you may ask me why this one has a naught, but then this one a naught is zero. Okay, in other words, this guy has an a naught. This guy does not have an a naught. It's because, right, if a naught exists, then it doesn't affect the reflection property of its graph. Okay, meaning okay, so the effect of a naught is to translate this up and down. Okay, translate it vertically. So even if let's say I started with let's say this original function, okay, and then I translate it up by a naught units, right? A naught. So that means the new graph will go up here. It is still symmetrical about the y-axis. So a naught, whether it exists or not, doesn't affect the reflective property. However, if a naught exists here, right? Okay, if a naught is non-zero, okay, if a naught is not zero, then the graph is surely not rotationally symmetrical about the origin anymore. Okay, that you don't have to understand this, but that's how I explain why there's no a naught there. Okay, it will not be rotationally symmetrical anymore. Okay, never mind. You don't need to really know those explanations. What you need to know at the end of the day is the definitions of Fourier's cosine, Fourier cosine, and Fourier sine. Okay, namely, Fourier cosine of a function is given by these properties. Okay, Fourier sine of a function is given by these properties. Okay, and then you have to know, main takeaway is this graph is even, so symmetrical about the y-axis. This graph is odd, so rotationally symmetrical about the origin. Okay, so let us investigate half-range expansions. Okay, so what is this topic? So for questions related to half-range expansion in exam, half of the periodic function is defined for you. Okay, for example, we're given a function f of x is equal to x defined for the intervals 0 to L. Okay, so what does it mean? You know that y equals to x, okay, y equals to x is a straight line passing through the origin. Okay, but in this case, this example defined it for 0 to L. Okay, so we only need to draw the graph between 0 and L. Okay, that's all. Everything else excluded. Okay, so yeah, we draw that first, which is shown here in this diagram. And then next, it says that we can extend the graph such that it may become even or odd depending on the question. Usually the question will ask to sketch the half range even or odd expansion. Okay, so it can be either half range even expansion or half range odd expansion of the graph over a desired interval. Okay, so the following steps are how to sketch a half range expansion. So let's say you are asked to draw the even half range expansion for this. Okay, for this uh function here. Okay, for this function here. Okay, so how do you draw the half range even function? Okay, so let us start out. Okay, they told us f of x is defined to be equals to x between 0 to L. Okay, so first we draw that. So this 0, this L, I'm gonna draw up like that. Okay, straight line passing through the origin. Now, if we are expected to find a half range even function, right? So what we need to do is, okay, remember the property of even function. Okay, I told you that even functions are symmetrical about y-axis. Okay, with this in mind, what you need to do is you reflect this graph on the y-axis. So you treat the y-axis as a mirror and then you reflect this. So if you reflect this, what would it look like? It will look like this, right? So this is half a period. Okay? This part is half a period. That's why it's called half range expansion. This is half a period. And then since we reflect it, this becomes one full period, right? One full period. So after it becomes one full period, this is the basic unit of one cycle. Okay, so one cycle of the periodic function looks like this. Okay, then what we need to do is let's say draw the half range expansion from draw the half range expansion from negative 2L to positive 2L. So what we need to do is we just copy paste this like that, like that, like that, like that. So up here will be, sorry, this is negative. You know what? Let me change the question. Let's say you want the half range expansion up to, let's see, negative 3L and 3L. Okay? So this is negative 2L, and here will be negative 3L. Yeah, so this is how you do it. Okay? So what the question will give you is this. And then what the question will ask of you is draw the half range expansion. So half range expansion means, first of all, you know that you want even function, right? Half range even expansion means it is symmetrical about the y-axis. So reflect it first. Okay, so you already reflected, right? So this will be one period. What you do is you copy paste until you achieve the desired domain that they want. So let's say they want the half range even expansion to be, okay, example, between negative 3L to 3L. Okay, so that means you just copy paste this. Okay, what I mean is copy paste this. Okay, copy paste this, copy paste this until you achieve 3L and negative 3L. So this is how you do an example of a half range cosine. Okay, so what about half range sine? Okay, so let's say you want to do the same example. Okay, let's say we're given the same function, okay? So hold on. So we are still given this function, right? But now instead of the half range even function, now I want the half range odd function, okay? The odd half range, okay? The odd half range, okay? So how do you draw that? So remember that for odd functions, it is rotationally symmetrical about the origin, right? So this is the origin. It is rotationally symmetrical about here. So what you need to do is this given graph, right? What you need to do is rotate it 180 degrees. Okay. If you rotate this 180 degrees, okay, this guy will appear down here. Okay, so this will be L. And then voila. So this is okay. So from here to here, this graph is one period. And then again, if you are asked to, let's say, do from negative 3L to 3L, what you need to do is copy paste until you fill up this entire domain. Let's say this is 2L, this is 3L, then here's 2L, this is 3L. So this thing, copy paste over this space until you fill it. So copy paste, okay, then copy paste. Okay, so now 3L until negative 3L until positive 3L has been totally filled by copy pasting one period, okay? By copy pasting the one period over the entire interval. Yeah, and that's an example of how you do the half range odd expansion. Okay? So that's just sketching it. Okay. We also need to obtain the f of x for these half range expansions. So to obtain the f of x for this half range expansion, right? What you need to do is use this formula. Okay. If you want the half range cosine expansion, okay, the half range even expansion, it will be this set of formulas. If you want the half range uh, odd expansions, it will be this set of formulas. Okay. Simple as that. Okay, so here's a FYI. Okay, the FYI is uh at discontinuities, right? If you want to, after you find that f of x, you want to find the value of this f of x at the discontinuities. Okay, then you will use this formula, okay, where x equals to a is a discontinuity. Okay, where x equals to a is a discontinuity. So what do I mean by discontinuity? What I mean by discontinuity is uh a break. Okay, a break in the graph. So just now, let's take a look at this. Let's take a look at the odd function that we draw just now. Okay, notice that this is a discontinuity, right? Because they don't join together continuously, right? This is where the graph breaks apart, okay? The graph breaks apart. In other words, when you approach from the left, there is some y value. And then when you approach from the right, there's a different y value, okay? This mismatch in y values is called a discontinuity. However, the f of x that you obtain, right, from the formulas, okay, after you do all the formulas, you will obtain an f of x. You can still find a value at the discontinuity. And that value, right, okay, so suppose that this discontinuity occurs at x equals to a, okay, that formula is given by, so if you want the value of the f at x equals to a, you can use the formula half limit as x approaches a from the right plus x approaches a from the left. Okay, and how would I find these values? This one and this one. I will take a look at the graph. Okay, you find these values by taking a look at the graph. Okay, so as I said before, uh, this here means the value of f of x as you approach x equals to a from the right, okay, from the right. So suppose that okay, suppose here is x equals to a, right? So this value is obtained by approaching from the immediate right of a, okay? So see, to the right of a, right, we have this line, okay? So let's trace along this line until we reach x equals to a, okay? So we are down here. Let's say this is -1, right? Then on the other hand, the x approaching from a negative, right, means you approach from the left. So you go to the left of this x equals to a, and then you move forward until you reach that point. Okay, so you arrive at this y value, and this y value corresponds to, let's say, 1. Okay, so that means this value down here is 1, and then this value up here, you get it as -1. Okay, so you substitute, and then you can calculate the value of the discontinuity. Okay, so that's that. Okay, so we need to know this additional info that can really help us simplify our Fourier series. Okay, this is especially relevant for Fourier cosine and Fourier sine. Okay, because of the graphical properties. So let me explain. So for two functions f of x and g of x, their product f of x, g of x follows this rule. Okay, so what did this table summarize? Okay, let's look at the first row. The first row says when f of x is even and g of x is even, the product of the two functions will be even. Okay, so even times even will give me an even function. Now let's take a look at the second row. Okay, so this one. So what does it say? This says that when f of x is even, g of x is odd, the product of the two will be an odd function. Okay, so even times odd will give me odd. Okay, and so on and so forth. Okay, so the third line says odd times odd will give me even, odd times even will give me odd. Now, how do you memorize this table? Okay, the way you memorize this table, right, is by remembering this, the sign rule for products. Okay, do you remember this from secondary school? You do, right? You, all of us are very familiar by now that a positive multiplied by a positive number will give me a positive number. Then positive times negative will give me negative, right? Negative times negative will give me positive, and negative times positive will give me negative. Okay, all of us knows this. Okay, how do I apply this to help me remember the odd and even function table? Okay, this is how you do it. Okay, so what you do is, let's take a look at the last sentence over here. The even odd table is just treating even functions as positive and odd functions as negative. Okay, it really does follow this pattern. Okay, if you treat, okay, if you think of even as positive, right, and then odd as negative, right, it will exactly match this property. So what do I mean? Okay, so remember we said that this is even. Okay, positive is even. Positive is even. Okay, so two positives multiplied together will also give me positive. And then we said by this logic, right, positive is also even. Now let's check if this uh, tallies with what the even and odd table says. See, even times even will give me even, right? Because you know positive times positive will give you positive. Now let's check the next line. In the positive negative table, it says positive times negative will give me negative. Okay, if we use this principle here, okay, what this is telling me is that even times odd will give me odd. Okay, let's see if this matches the results in our table. Yes, even times odd will give me odd. Okay, then what about the next line? The next line says minus minus give me plus. So this, by this logic, right, it will say odd times odd will give me an even function. Let's see if it tallies. Yes, it does. Then finally we have negative positive will give me negative. So this is saying odd times even will give me odd. So it does tally. Okay, so right, all of us are very, very, very familiar with this table already. Plus times plus is minus, sorry, plus times plus is plus, plus times minus is minus, minus times minus is plus, minus times plus is minus. Okay, all of us are super familiar with this already. So the next step to remembering this table, right, is simply remembering that even corresponds to the plus and odd corresponds to the minus. Okay, then you can just swap out all positives with even function and all negatives with odd function. Okay, all the negatives correspond to odd function, all the positives correspond to even function. And then you will remember this table. Okay, so why is this helpful to remember? Okay, so let's take a look in the next page. Okay, so how is the even odd table useful to simplify Fourier series? Sometimes you need to integrate the product of two functions, okay? So yeah, you need to integrate the product of two functions. And this can be very complicated, okay? An example here is integrating, okay? So you're integrating x squared cosine x, okay? So this is kind of complicated to integrate. So can we make our life easier? Yes, we can, okay? Yes, we can. So we want to integrate, okay? Let's see. Yeah, okay. So let's say we're integrating from negative L to L, okay? Negative L to L of that function, x squared cos x dx, okay? So let's investigate. Here, this is a product of two functions, this function and this function. Now let's check. Are these functions even or odd? Let's identify. Okay. So x squared, as we discussed before, this is an even function. Cosine x, okay, you must know that this is an even function. Now, multiply them together. Even times even, okay? Remember, plus times plus will give me plus. So even times even will give me even. So collectively, this entire function is effectively an even function. Okay, this entire function is an even function because x squared is even, cosine x is even, so even times even will give me even. Okay, the entire thing is even. Since you know that this is even, right? Okay, what is the graphical property of even functions? You must remember that the graphical property of even functions is that they are symmetrical about the y-axis. Okay, symmetrical about the y-axis. How is that helpful? Okay, so we don't know what the we don't know how exactly this function looks like, right? But never mind. That's not the point. Okay, so let's say it's like this. Okay, I'm not being accurate here. So let's say this is x squared cosine x. Okay, we don't care what the graph looks like. What we care is that we represent it as symmetrical about the y-axis. Okay, the point is that you must represent as symmetrical about the y-axis. So this is negative L, this is L, right? If we integrate it from negative L to L, we are finding the area under the graph like this. Okay, so how can we simplify our life? If we know that it is symmetrical about the y-axis, right? Agree with me that this yellow area will be equal to this green area, correct? Okay, these two areas are equal because it is symmetrical over the y-axis. So that means, right, instead of integrating from negative L to L, what I can do instead is, okay, so negative L to L, x squared cosine x will give me this total area. But instead, what I do is 2 times 0 to L x squared cosine x dx. Okay, so what does this state? What is integration of that function from 0 to L? Okay, so let's take a look. So integration from 0 to L, right? Integration from 0 to L means the area under the graph from x equals to 0 to x equals to L. So this one only, right? And why did I take times 2? This time 2 is because this side, okay, the red shaded part which I already ignored, is identical in area. Since it is identical in area, you just take this side, multiply by 2. Okay, so in essence, right, what I'm saying is that what we want, right, what we want is integration from negative L to L. So this entire area. But what we do instead to simplify our life is you take 2 times only half of it, 0 to L. Okay, this will dramatically simplify our integration. Okay, dramatically simplify by integration by using this version of the integration. Okay, you'll see what I mean when as we go through the example. Okay, yeah. Yeah, so that's for even function. So this is here. So for example, when you want to integrate that thing I'm talking about, you identify that x squared is even, cos is even, so even times even is even. Yeah, and then you can simplify it by taking it through this. Now, suppose that the function is effectively an odd function. Okay, it's an effectively an odd function. Okay, we know that the integral from negative L to positive L must be 0 because the positive area cancels with the negative area. So this one is the positive area, whereas this one is the negative area. Okay, so now let's take a look at the. Okay, notice that, you see, this graph that I draw here, this one, it is rotationally symmetrical about the origin, right? It is rotationally symmetrical about the origin. Okay, so when you integrate from negative L to L, this area is effectively, okay, the net area is 0. Okay, because the positive area added with the negative area will become 0. So I'm going to talk about this in more detail with this example. So let us do this example and see how can we simplify it. Negative L to L sine x cos x dx. So this is a product of two functions, namely sine and cosine. Okay, so sine times cosine, will it give us an even or odd function? So as you know, sine is an odd function, cosine is a even function. So remember, we treat odd as negative and even as positive. So minus times plus will give me minus. So that means odd times even will give me odd. So collectively, this will be an odd function. Okay, so what I'm seeing here is an odd function. As you know, odd function, right? The property of odd function is such that it is rotationally symmetrical about the origin. Okay, so let us draw a graph that is rotationally symmetrical about the origin. So I don't know how sine x cos x looks like. I don't care. The most important part is it is rotationally symmetrical about the origin. So let's say it looks like this. Okay, and this is rotationally symmetrical about the origin. Okay, so this is negative L, this positive L. Integrating from negative L to positive L of this graph, right? So this represents sine x cos x. It's not accurate, okay? I'm just simply drawing. But the most important property that you must retain is that it is rotationally symmetrical about the origin. Okay, integrating this means I want to find the total area on this here, right? But you see, the thing is that this area, okay, this area is the negative version of this area. So what do I mean? Let's say, right, the area of the positive part is 10 units, right? That's the area of the positive part. But what about this part? If that one's 10, and then this is rotationally symmetrical, right? Then this will be negative 10 units. Okay, so that's what it means. Integration means you sum up the area. So if you take negative 10 plus 10, then altogether, the net area is 0. Okay? Yes, the net area is 0. Okay? The area of this, right, is negative because it is under the x-axis, right? Under the x-axis, the y values are negative. So that means when you find the area, okay, when you integrate from negative L to 0, this will be a negative area. Negative area. Okay? So when you add this up, it will effectively be 0. And this really dramatically simplifies our life, right? If you know that this is 0, right, then you don't need to do any calculations. You don't need to do any integration. You can straight away tell me that this is 0. Straight away, without doing any working in between. No need for working. No need. Once you know that it's odd, and then you're integrating over one period, right? Straight away, it will become 0. That is really how this simplifies our life by so much, okay? You don't have to do integration. You can straight away tell me if you're integrating an odd function uh, from negative half a period to positive half a period, then it is 0. Okay, straight away it is 0. Okay, so as you can see, we cleverly skip the integration once we know this trick. Yeah. So okay, so this summarizes the theory behind Fourier cosine and Fourier sine series. So in the next set of videos, I'm going to talk about the tutorials.